We've been talking a lot about error associated with prediction. Now we'd like to talk about a statistic to quantify that amount of error. It's called the standard error of estimate.
We've actually mentioned the standard error of estimate in a few earlier videos. Let's bring ourselves up to date here. Here's the correlation between skin folds and percent fat. Here was the equation for a straight line. Here again was the line of best fit and how we could predict from any given x to the outcome variable y. Let's take a look a bit more at this graph for just a second. Here's the same graph, but notice here there are lots of errors in the prediction. If you predict from the equation with the straight line, very few points actually fall on the straight line. So each one of these little deviations from the line represent prediction errors. So all of those are prediction errors. There are very few scores that fall really close to the line, so there will be errors in prediction. That error in prediction is called the standard error of estimate. It's the standard error, SE, or the standard error of estimate, SEE, or the standard error of prediction, SEP. They're all the same thing, but importantly, the standard error of estimate, or the standard error of prediction is a standard deviation. It's the standard deviation of the errors of estimating y from a given x. It's based upon the standard deviation of the y's and the correlation between the x's and the y's. The higher the correlation, the less error in prediction that there will be. Let's illustrate that here. Here we have the correlation between skin folds and percent fat. We have the regression line or prediction line represented in yellow. We have a prediction for a given person on x, and that value is then predicted on y. But notice there's variability around the predicted value. And notice we have overlaid a normal distribution with standard deviations. Those standard deviations, in this case, are standard errors of prediction. Now we put in a few values that might be used to estimate. So, for example, if your skin fold was 40, you substitute into our equation, and you would have a predicted percent fat of 20%.
If your standard error of estimate is 3, one standard deviation from the value of 20 would be 23 or 17.
If you think of it, the value of 20 is actually the mean. It's the mean on y for those people who had a same value on x, in this case 40. But there's some error around that. Think back to the normal distribution now. This is a normal distribution with a mean of 20 and a standard deviation of 3. So the chances are 68 out of 100 that the person with an x value of 40 will have a y value between 17 and 23. That's no different than what we did in the normal distribution examples. So here we are again. It illustrates the same thing. What's the predicted y? Well, y hat is equal to bx plus c. In our equation, b is actually 0.25, c is 10. So how did we get 20? We substitute 40 into our equation, and the predicted y hat, the predicted percent fat, was 20. But there will be some error. The errors of estimate is the standard error of estimate. So for example, sy dot x, the standard deviation of y for a given x, is equal to the standard deviation of y times the square root of 1 minus the coefficient of determination. If the standard deviation is 7 and the correlation is 0.9, notice as we substitute into the equation, we get the standard error of estimate to be 3% fat. So let's use a couple of examples now. Here we've added in the same picture, but now we've added 2 standard deviations, or 2 standard errors. So the predicted value was 20. If you go up 2 standard deviations,
then 95% approximately of the people with a skin fold of 40 would have a percent fat prediction between the values of 14 and 26.
Notice there may be few or none who have an actual value of 20, who have an X value, 40 millimeters of skin fold thickness. How do we do this? Go right back to our z-score example again. Z is equal to X minus the mean divided by the standard deviation. Remember now, the mean value here is 20. It's the mean value on y for those people with a given value on x. 26 minus 20 divided by 3. So the score of 26 is 2 standard deviations above the mean. No difference here than what we did in the z-table. Therefore, how likely is it that a person with 40 millimeters of skin fold thickness would have a percent fat of greater than or equal to 26? 50% minus the 47.5 says that the chances are only 2.5 that a person with 40 millimeters of skin fold thickness will have a percent fat of 26 or more.